Okay, so welcome to the lecture 58 in the course Classical Mechanics 1, and we were discussing the small oscillation. So in last lecture we have developed the method how to find the frequency of small oscillation in a general system, and we have seen that the determinant Vjk minus omega square T jk, this determinant of this matrix equation will be 0 to find the omega square, that frequency omega of the omegas of the system. System was described, let me write the Lagrangian. So this was our jk sum over jk qj dot qk dot minus half sum over v jk qj qk, no dot here. Okay. So this we did in last class. So this is the Lagrangian, and for this system, so frequency of small oscillation can be obtained by considering this equation. And when the solution, general solution Qj will be given in terms of some general solution I omega t minus delta j of this form. Okay. So now purpose of this lecture will be that we will consider an explicit example to understand whatever we have what we have discussed in last lecture. So example, and I hope to finish this example in this. So this is a well known problem of two coupled pendulum connected by a spring. So this is pendulum 1, this is pendulum 2, and let us say this has length L, mass m, this also has mass m. This is rest length between these two point of support is a distance between the point of support is a. Let us consider this point is origin. Okay, and these two mass point are connected by a spring. Okay, and let us have the spring constant k. Okay, so and this is your x direction, and this is say y direction. Okay, so this is the system, and we'll try to find the frequency of small oscillation of this coupled system. Okay. So let us first construct the Lagrangian of the system, and for that purpose we write the coordinate of this is x1 y1 and coordinate of this is x2 y2, and as you know that kinetic energy, we have to find Lagrangian, we have to find the kinetic energy and potential energy. So kinetic energy for first particle will be half m first pendulum x1 dot square plus y1 dot square. For the second one will be half m, both having the same mass, so x2 dot square plus y2 dot square. And the potential energy, so notice here we will have gravitational potential energy as well as you will have the potential energy due to spring. So gravitational potential energy, okay, so now to solve this problem we have to find that how much this mass has raised while oscillating. Okay. So in all pendulum problem, as we consider the angle of oscillation, so let us consider this angle is theta 1, describe the angle of oscillation for the first mass. Similarly, for the second one, it's, let us denote this angle 2. So, you can see that if we make a triangle out of this, then you can find this distance, this much distance. Suppose this is equilibrium position. Suppose this is equilibrium position. So, this distance, this mass has raised. So, the potential energy for the first one will be mg, and L minus L, this distance is L cos theta 1. So, L cos theta 1, okay, or that is basically y 1. So, this is y 1, and for the second one it will be mg, it will be L minus L cos theta 2. This is exactly similar, okay, and the spring energy will be half. So, let us k is the spring constant, it is r minus a whole square. I wrote in this form because, okay, it will be convenient for our mathematical purpose. So, where r is basically the length of the distance between the two mass points. So, r is basically x2 minus x1 whole square plus y2 minus y1 whole square. And if you from this geometry, we can write that your x1 is L sin theta 1, and y1 I already wrote, use cos theta 1. Similarly, x2 will be a plus L sin theta 2 plus y2 will be L cos theta 2, okay, because this distance is your L sin theta 2, okay, and A is the distance between the two point of support. Okay. So, let us calculate. So, the Lagrangian is your kinetic energy minus potential energy, okay, for sure. So, let us calculate the different terms. For example, if we calculate the kinetic energy term, x1 dot square plus y1 dot square. So, it is very simple. So, it will be kinetic energy term will be half m L square theta 1 dot square, okay. Similarly, the second term will be plus half m L square theta 2 dot square, okay. Now, potential. So, this is our let us so this kinetic energy term is simplified. It is very so just make a write a let us put few equation, because this will help in, okay. So, this may be equation 1, potential energy may be equation 2, R expression equation 3, this relations are equation 4, okay. Okay. So, now potential energy. So, potential energy, let us simplify, mg, if I take L common, 1 minus cos theta 1, okay, is can be written as mg L cos theta. We can now theta 2 are small, assuming, so we can have a approximation that, okay. So, later we will have, so together. So, this plus mg L 1 minus cos theta 2, okay. So, this we can write, suppose these two potential energy, k minus a term will simplify separately, okay. So, this will give you 2 mg L, this one from this term, one from this term, and then minus mg L, and cos theta we can write 1 minus theta 1 square by 2. So, minus mg L 1 minus theta 2 square by 2. Okay. So, basically 2 mgl will get cancelled and you will get mgl by 2 theta 1 square plus theta 2 square. Okay. So, in the small angle approximation. So, let us denote this part as equation 5. So, some part of the potential energy we have calculated and that we find equation 5. So, now r minus a part. So, r square is basically r square is x2 minus x1 whole square plus y2 minus y1 whole square. Okay. So, x2 minus x1, so look at this x2 minus x1 is basically you will have a plus L sin theta 2 minus sin theta 1 and its whole square plus L cos theta 2 minus cos theta 1 whole square. Okay. So, if I break this square, it will be a square plus L square then sin theta 2 square sin theta 1 square minus 2 sin theta 1 theta 2 plus 2a L sin theta 2 minus sin theta 1 and the other term will be L square cos square theta 2 plus cos square theta 1 plus 2 cos theta 1 cos theta 2. Okay. So, now if I consider the small theta approximation, this will be a square plus L square and sin square theta will be theta 2 square, theta 1 square will be theta 1 square because we are taking sin theta approximately equal to theta, cos theta will be 1 minus square by 2 square. This approximation we are considering. So, times 2 theta 1 theta 2, okay. L square is outside plus 2a L theta 2 minus theta 1 theta 2 minus theta 1. Now, from this term L square there is a minus, yeah. So, this make a correction, this will be minus. Okay. So, it will be a 2L square, how we get, okay. So, this will be L square 1 plus theta 2 square plus 1 plus theta 1 square by 2 and then minus 2 times. So, this 2 times 1 plus theta 1 okay, minus 2 times theta 1 now if I can keep the cos theta 1, okay. So, let me write theta 1 square by 2 into 1 minus, this is a minus, I am sorry. So, this is minus 1 minus theta 2 square by 2. So, this little bit simplification, we need a square plus here we need L square theta 2 minus theta 1 whole square. So, up to this term plus 2 a L theta 2 minus theta 1, okay. And the rest of the term let me check, they will simplify. Yeah, so they will cancel here. So you can see theta 2 minus theta 1 is basically you can cancel. See, you can have a cancellation. So L square is outside. So theta 2 square with a minus sign, you will have a minus, then you have theta 2 square by 2. So this term will cancel, and you will basically up to this term. You just check yourself that this term will cancel to give you this term. So this is basically a plus L theta 2 minus theta 1 whole square. So what I have not shown explicitly, that these terms with the small theta approximation will be 0, okay. And then you have, so this is your note, this is my r square. So r is a plus L theta 2 minus theta 1. So r minus a is basically L theta 2 minus theta 1. So now I have simplified all the terms. So this equations maybe 6. So let us go back. Yeah. So now if I collect all the terms in kinetic energy term, then potential energy term from equation 5, and then this equation 6. So my Lagrangian will be, let me write, final Lagrangian for this will be half m L square theta 1 dot square theta 2 dot square. This is kinetic energy term. And then potential energy term half k L square theta 2. So I have to collect from mg L by 2 theta 1 square half k, from where the, okay, k will be coming from, okay. So the order of term has changed. Let me write, okay. So first we will write that equation 5, mg L by 2, so minus mg L by 2 theta 1 square plus theta 2 square, and then minus half k r minus a whole square. So r minus a whole square is this, plus theta 2 square plus theta 1 square minus 2 theta 2 theta 1, okay. So this will be the full Lagrangian. So let me write this Lagrangian in a simplified version, and we will see what will be the T matrices and V matrices of this system. So m L square theta 1 dot square plus theta 2 dot square minus theta 1 square. So let us collect. Theta 1 square is appearing in two places, here and here, both has minus sign. So mg L by 2 plus half k L square theta 1 square minus mg L by 2 plus half k L square theta 2 square, and there is a theta 1 theta 2 term which is with a plus sign, plus k half k L square 2 theta 2 theta 1. So this is my full Lagrangian, okay. So let me write my T matrices. I can identify immediately the T matrix. T matrix will be only no cross term. So T matrix is a diagonal in this case. So it's m L square 0 0 m L square, okay, and okay, that's fine, that's all. And V matrix will be theta 1 square is diagonal, so it will have m theta 1 square will be in the 1 1 position, and half I can take half is the in that definition you have. So, mgl kl square will be this term. So, ml square g by l and k plus k by m, okay, I think is correct. And also theta 2 is also same. So, mgl plus kl square, and theta 1 theta 2 we have to be symmetrically. So, it one place it will be kl square minus, because this has a plus sign. So, it will be, and this will be kl square. Okay. So, let us write this is equation 7. When we have T and V matrices, we have equation 7. Okay. So, this let me write T matrix as ml square common. So, it is 1 0 0 1, and V matrices also we take ml square common. So, it will be ml square. So, it will be k by m plus g by l, and this will be minus k by m. ml square I am taking common in both T matrices and V matrices for convenience. Okay. And then it will be again minus k by m, and it is also will be k by m plus g by l. Okay. So, this is equation 8. Okay. So, now if I put the condition, remember the condition V minus omega square t determinant equal to 0. Okay. So, this condition if I put and ml square take outside. So, I have ml square V matrices is omega square t. Okay. So, V matrices k by m plus g by l minus omega square coming from the T matrix part, and this term also will be k by m plus g by l minus omega square, and these are off diagonal terms will be minus k by k. So, determinant of this equal to 0. Okay. So, you can immediately find that k by m plus g by l minus omega square whole square minus minus minus. So, 3 minus k by m whole square equal to 0, this determinant. And now, if you solve for omega, you will find omega will be g by omega square will be g by l in one case, and in other case omega square will be g by l plus 2k by m. Okay. Yeah, that means first solution omega 1 we find root g by l, and omega 2 we obtain as g by l plus 2k by m. Okay. So, these are the frequency of oscillation for this system, and one can find the eigenvectors. So, let us find the eigenvectors also. For example, when omega equal to omega 1, so let us, these eigenvectors are denoted by a1 and a2. So, immediately I can write g by l plus k by m minus g by l, this is omega 1 square, and minus k by m minus k by m, and g l plus k by m minus g by l. See, omega 1 square is g by l. So, that I have written, and a1 a2 will give you omega 1 square, no, that we have already taken, so will be equal to 0. Okay. So, this is equal to 0. So, you will find so k by m of 1 minus k by m of a2 equal to 0 and minus a1 plus a2 k by m equal to 0. That means a1 equal to a2. So, both these equations implies a1 equal to a2. So, for omega equal to omega 1 equal to root g by L, this frequency we find the eigenvector is kind of a11. Okay. Similarly, you can find omega equal to omega 2. The equation will be, so this is the eigenvector. So, let me write this is the eigenvector equation, say 8 or 9. Let me 9. So, this is my equation 9, and for omega 2 we will find the exactly same fashion. So, g by L plus k by m minus omega 2 square g by L minus 2 k by m, and this side k by m minus k by m. So, g by L plus k by m minus g by L minus 2 k by m, and say this vector is b1 and b2 equal to 0. Okay. So, g by L get cancelled, k by m. So, I have minus k by m all places. So, let us take minus k by m outside, then it will be 1 1 1 1 everywhere, and b1 b2 equal to 0. So, this means implies that b1 equal to minus b2. So, for omega equal to root g by L plus 2 k by m, this solution, the eigenvector is b1 minus 1, and you can see they are orthogonal, but they are not normalized. Okay. So, maybe we do not have time now. So, in next class, so we will explain how to normalize this solution. Okay. Orthogonality, you can check that your a11 and b1 minus 1, these are orthogonal, right. So, you can find that these two are orthogonal. So, we have found in this lecture the eigenfrequency of the system of the coupled oscillator we have considered. Okay. So, in the next class, so you have only 2 more lectures. So, plan is that in next lecture we will find how to construct the orthonormal eigenfunctions, and then we will consider the oscillation vibration in a carbon dioxide molecule. So, you will find that this theory can be applied to study the vibrational frequency, to calculate vibrational frequency of carbon dioxide molecule. So, in next class we will continue with this, find that how to find normal modes, normal coordinates by orthonormal condition of this, and then we will consider carbon dioxide molecule, and then last lecture maybe we will consider few more examples as a tutorial class, and that will conclude this course. Okay. So, bye for now, and we will start from here in the next lecture.